another polar problem. There's on my work for that if you just need to check a certain part. For part A, there's a couple ways that you can think about this. What I always do is when they give me these angles, I like to draw those angles in and think of those as like windshield wipers that take me across my bounded area right there. So we're going to use our polar formula for a polar area is 1/2 times the integral of r squared. And so here's what I'm doing for this first integral. I'm going to focus on this top little sliver, right? When I use that top little sliver, I go from this windshield wiper just to this windshield wiper, from pi over 6 to 5 pi over 6. And that's using this like bigger equation, this apple looking equation. That's a harder looking equation. So I'm going to use 1/2 r squared with that equation in between the pi over 6 and the 5 pi over 6. That's what I did right there. And that's going to give me that top shaded area. Now the rest of it, we're going from this windshield wiper all the way around to this windshield wiper, and you're just on that circle that r equals 3. So one way you can do it is go from the 5 pi over 6. Now you got to be careful. You don't want to go from 5 pi over 6 to pi over 6. That doesn't make any sense, right? You're going to go from 5 pi over 6. If you did go all the way around and stop it on that x-axis there, you know that x-axis is 2 pi if you went the whole way around, which is 12 pi over 6. So if you went an additional pi over 6, that will place you at the 13 pi over 6. So you could go from this windshield wiper to this windshield wiper to get the whole bottom area from 5 pi over 6 to 13 pi over 6 using that 1/2 r squared, but that's just with that r equals 3 equation. So you're using that. All right, so there's two different math nines in the calculator to get you that number there. You have to show the setup of your integrals, and then they know you're using the calculator to get that. But this is your justification. If you just have this, you're not going to get full credit for it. You have to give me the setups with the integrals there. Now, another way that you could do that, you could just find this little slice of the pie from 0 to pi over 6. And then that's 1/2 r squared from 0 to pi over 6. You could then realize this is symmetrical. So if you double it, you got this slice of the pie, this slice of the pie. That'll get you that part. And then that's still this whole bottom semicircle, which is as pi r squared divided by 2. Either way, so if you plug this into the calculator, you're going to get the same decimal answers. If you plug this into the calculator and you add it to that little sliver part, there's your polar area. All right, now for part B, it tells us theta equals t squared. So that means I'm probably going to take that t squared and plug it in for the theta at some point. And then it says find where the x coordinate position is equal to -1. So again, if they're talking about on these polar problems, they're talking about an x getting involved or a y getting involved, that's simply your pre-calc stuff, right? So x is r cosine of theta, y is r sine of theta. And so I started with x equals r cosine of theta. I plugged in the r that they told me to use. And then they told me theta equals t squared. So I plugged in the t squared to all of those. And then they tell us the x coordinate is equal to -1. So I need to plug in the -1 for that x. Now, anytime you have a complicated equation to solve, here's where the really good technique is. We're on the calculator part of the test, right? So I do not have to waste my time trying to figure out how to solve this thing algebraically. Even if you could, it's probably going to take you too long there. So if you have ever a complicated equation to solve and you're on the calculator part of the test, move everything to one side. I move the 1 over there, set it equal to 0, and then graph this function in your graphing calculator. So I already kind of did that for us. You can watch that graphing calculator video if you want a little bit more detail, but I already put that whole function in there. You see that it's already in radian mode. Careful with my parentheses. Now, when I have a trig graph, first thing I did was hit zoom 7, and it was a very chaotic looking graph. And then after I hit zoom 7, I then hit my window button and I changed my X-min and X-max from 1 to 2 because it gives me that interval to use. And so I only care about that interval. So now when I graph it, there's only one spot where that graph is equal to 0 and the calculator will find it for it. So remember what you do is you hit the trace button, put your cursor somewhere in that vicinity. You're going to hit second trace, brings up your calculate menu. You're going to hit number 2 where it says calculate the 0. The left bound, you have to make sure the cursor is to the left of that 0. So in this case, on a decreasing function, we got to make sure it's above the x-axis there. So I'll hit enter on that. Right bound, you have to move it over to the right, and you got to make sure that y value is changing sign to go to the right of that x-intercept, to the right of that 0. So make sure that y point changes sign. So I'm gonna hit enter on there. And then for the guess, I just hit enter a third time. You already narrowed it down. And so I'll hit enter a third time. And then that's how I'm getting this 1.428 number right there. But you have to show your work. You gotta show your setup. And then they're expecting you to use the calculator to kind of get that number right there. All right, now for the last part, it says find the position vector in terms of t. Now position, they want to know, you're talking like x comma y, all right? And then x and y, your x is r cosine of theta, your y is r sine of theta. So then I went to that, and then they told us for the r, it says for the particle described in part B, which is just using that r right there. So I took that r and I plugged that in for both of those. And then again, it says in terms of t, and they tell us in that part B that theta is t squared. So I just replace the theta with the t squared. So there's your position vector right there. So that's the first part of it, is they wanted that. And so it's just x comma y. And then like your velocity would be like x prime, y prime. Your acceleration would be x double prime, y double prime. But there's a position, there's in terms of r's and thetas, and then you get your t's involved. And now we want to find the velocity vector at this time. So I'm so grateful they gave us a time interval right there, because otherwise I'm not able to plug it into the calculator unless they give us a time interval, a time number right there. Then I would have to take a bunch of these derivatives right there. But see, now if that's my position, I want to go to the velocity. That means I need to take the derivative of that, evaluate it at 1.5. I need to do the derivative of that, evaluate it at 1.5. The calculator will do that for us. That's the math 8 function. So so I'm going to come out here now. I already got this set up for us. All right, so I want to take the derivative of this function. So I hit the math 8. There's my derivative notation. And there you can see how I entered all that in. And so you entered that in right there. You don't take the derivative in, and you entered that in. It'll take the derivative for you, evaluated at 1.5. So notice when I hit enter right there, it takes that derivative for me, and then I'll be able to get that negative 8.072 number. Always round to 3 numbers after the decimal. And then I'm going to do the same thing. I'm going to go up in there, and I'm going to hit enter on that. And all I got to change for this second part, this first parenthesis stays the same. I'm just going to change the cosine to a sine for that second part. So I'm going to go in there and then change it. I'm going to hit the sine button and then evaluate that at the 1.5. And then you're able to get that negative 1.673 number. Comfy couch and love seat.